modulo or multiplication modulo. So in the introduction already I have told that is what is additional modulo m or multiplication modulo m. Okay, how we will represent that one? So that we have seen. So same thing we will learn here with the help of one problem. Okay, so addition and multiplication modulo. Multiplication modulo m or n. Okay, in some books you will have m, or in some you will have n. Anything you can take. Okay, m is here is integer. Okay, so there are two special types of operation: addition modulo n, written as, so addition modulo n, addition modulo n, written as. So in three different ways we'll write that one. That is plus mod n, or we'll write as like this, plus m. Okay, or simple plus m, like this. Okay, so multiplication modulo can be written as multiplication modulo n, written as into mod n, or into circle n. Okay, or into n, like this. So this is the representation of addition modulo and also multiplication modulo. Okay, so these you will do on the set of integers, that is z or I. Okay, so even you can write this as whenever a and b are any two integers, small a and small b be any two integers, and n be a positive integer greater than 1. So whatever the n value you are taking here, it should be always greater than 1. So in the addition modulo, n of a and b is defined as the least non-negative remainder are obtained when a plus b is divided by m. Okay, so this definition you can see in your textbook. So we'll write this as addition modulo a plus nb equals to r. Okay, so where r is 0 less than or equals to m, and here we'll write it as a cross nb, that is equals to r, where say 0 less than or equals to r, less than or equals to m. Okay, so where here r is the remainder obtained by dividing the usual product ab by m. So here whatever r is there, that you will get as a plus b divided by n. Okay, so here whatever r is there, r is equals to ab divided by n, where r is here remainder. Okay, so where this r is the remainder we have. So whenever whatever the two integers are there, when the two integers are divided by n, we get the resultant, that is the remainder here. Okay, so you can take the examples here. So 5 modulo 4 plus modulo addition modulo 4 plus 5 is equals to. So here what we have, when it is addition modulo, it is a plus b by n. So a plus b means 5 plus 5. What is our n? N value is 4. That is 10 by 4. Okay. So what you will get remainder? 4. 2 times 4 to the 8. So remainder is here 2. So here the resultant is 2. Okay. So this is R. This is A. This is plus of n. This is B. Okay. So addition modulo 4. Whatever the resultant you are getting, that is the remainder. Okay. So similarly, you can do for multiplication also. That is 3 multiplication modulo 5, 8. 3 8s are what we will get? 24. So whatever the resultant you are getting, that you have to write. So 3 into 8 by 5. So 3 8s are 24 by 5. So whenever you will divide by 5 5s are 25, but we have in the numerator 24 more. So 5 4s are 20. So what is the remainder you are getting? 4. So this is the resultant here. So this is R, small r. Whatever we are getting the resultant, that is called as a remainder. So like this additional modulo or multiplication modulo we will find like this. So on this addition and multiplication modulo, we'll have the problems to find any of the integer value will be given, that is Z10 or Z8 like this. Is whatever the integers are there, they will be in the form of 1, 2, 3, 4 up to n minus 1 elements. Okay. So one set will be given. From that set we have to find, we have to show that it is an abelian group with respect to of multiplication modulo 10. Okay. So in the question it will be mentioned with what that is the n value will be given in the question, and it will be mentioned whether it is addition or multiplication modulo, and even the set will be given. From these all you have to find, means in the question if it is mentioned abelian group, it may be mentioned group or it may be semi group like that. So depending on that you have to solve the problem. Okay. So this problem we have, prove that Z10 is equals to 1379 is an abelian group with respect to multiplication modulo 10. Okay. This is the problem we have. So prove that Z10 is equals to, that is 1379 is an abelian group. Is an abelian group with respect to multiplication modulo 10. Okay, here n value is 10. Okay, so first for finding this one, whenever it is asked like this, first you have to frame the composition table. Okay, so multiplication is the operation here. With respect to of that, you have to find the composition table. Okay, solution. So given Z10 is equals to 1379. Okay, so composition table, or we call it as Cayley's table. Composition table or Cayley's table. Okay, so this concept you have even in 10th class and also intermediate we have this one. Okay, so first on the rows and also columns, whatever the elements are given in the set, that you have to write. Here whatever the operation given in the question, that operation you have to write. Okay, next 1 3 7 9 1 3 7 9. So with respect to of the operation, you have to find the values here. Okay. So 1 into 1 is 1. So first row, this first row and also this column, you will get the whatever the elements are there, those same you will get. Why? Because you are multiplying with 1. So 3 into 1 is 3, 7 into 1 is 7, 9 into 1 is 9. Okay, now 3 ones are 3, we got 3 threes are 9. Okay. Next 3 sevens are 21. So just now we have seen here multiplication modulo, no? So 3 sevens are 21. 21 by divided by n value is 10. So 10 twos are 20. What is the remainder? 1 will get here. Okay. Next 3 nines are 27. 27 by 10. Okay. Means how many times you will get? 10 same 2 times. So 7 you will be the remainder. Next 7 ones are 7 we have written, 7 threes are 21, just now we have seen, no? So 1 will be the remainder here. 7 sevens are 49, 49 by 10 means 10 fours are 40, 9 will be the remainder. 7 nines are 63, 63 by 10 means 10 six are 63 will be the remainder. Next 9 threes are 27, 27 means what we got? 9 threes are 27 means 7 you will get. Next 9 sevens are 63 means 3 you will get. 9 nines are 81 means 1 you will get. Okay. So like this you have to find the composition table depending upon the operation. If it is addition, that modulo you have to find. If it is a multiplication, that modulo you have to find. Okay. Now in the question it is asking to show that it is an abelian group. So when we have to show that abelian group means it should have to satisfy first thing is a closure property. Next second one is the associative property. Third one is the identity property. Fourth one is the inverse property, and fifth one is the commutative property. So if these 5 properties are satisfied by this composition table with respect of multiplication modulo 10, then if it is satisfying all the properties, then only we call it as an abelian group. Okay. Okay, now you are able to see there is an abelian group with respect to of multiplication modulo n. First property is the closure property. What is closure property? Whenever 2 elements are taken from the given set, when you do the multiplication of that one, if you get the same element, whatever present in the set, then we call that it is satisfying the closure property. Okay, you can take any 2 elements, 1 and 3 are there. 1 into 3 is 3. 3 is present in the set, no? So therefore, it is satisfying the closure property. You can take one more example. 3 sevens are 21. So with respect of modulo 10, not directly, with respect of, that is modulo, multiplication modulo 10, you are getting the resultant as 1. So 1 is present in the set. Therefore, it is satisfying the closure property. You can check any numbers. Okay. So first one is closure property. Closure axiom. So that is all the entries in the table are the elements of Zn. So whatever the numbers we are getting in the composition table, these all elements are present in our given set. Therefore, other than this, if other than these 4 numbers, if you are getting any other number, then we call that it is not satisfying the closure axiom. But here, whatever the numbers you are getting in the table, those are the elements of the given set. Therefore, it is satisfying the closure axiom. So, all the entries in the table are the elements of Zn. Okay. What is Zn? Zn is 1, 3, 7, 9. Okay. So therefore, the closure axiom is satisfied. Therefore, closure axiom is satisfied in Zn. Okay. So this is the closure property. So after this closure property, we need to find the associative property. So associative property means we know 3 elements we have to take, and you have to find A cross B cross C and also A into B cross C. If both you are getting the same, then we will tell that the associative property is satisfied. Okay. So associative second one is, so associative axiom is consider, okay, you take any three elements. We need ABC, no? Three elements means 137 or 139 or 379. It's your wish. You can choose any three numbers, okay? So 1, okay? So this is A cross B cross C. So whatever the resultant, you will get 3 into 1 is, that is 1 into 3 is 3, into 10 into 7 is equal to 3 sevens are 21. So with multiplication 10 means you will get the value as 1. Okay. So next A cross B cross C. So A cross B cross C. Okay. So 1 into 3 sevens are what will get 21. 21 means you will get the remainder as 1. So this is equals to 1. Okay. So therefore these two are equal, no? So therefore 1 is equals to 2. Therefore associative axiom is satisfied in Zn. Okay. So next is the identity. Third one. So identity means, so identical means here whatever the row is there. So this is the, we are writing the first row, no? Whatever the second row is there, this is same as the first row, no? Second row is same as the first row. And even here, second column is same as the first column. So whenever you will get the like this element same, then we call it that it is satisfying the identity property. And even you can see here, whenever we'll do 1 cross 1, you will get 1, no? That means it is the inverse property. But whenever whatever given first row elements and given first column elements, you are getting as the identical one with respect of the given row and also column, then we call that it is satisfying the identity property. Okay. The row leaded by the element 1 is identical to the top row. The row leaded by the element element 1 is identical to the top row. Okay. Therefore, 1 is the identity element. Okay. And we know that this 1 belongs to Zn also. Okay. 1 is present in the set Zn. Okay. So here with respect of 1, whatever we are doing, we are getting the same identical element here. So with respect of 1, 1 ones are 1, 1 threes are 3, 1 sevens are 7, 1 nines are 9. So what is a multiplicative identity? A into 1 is equals to 1 into A is equals to A. Okay, this is the identity property with respect of multiplication. So 1 into 1 is equals to 1. And also if you do the reverse same, even 1 into 3 or 3 into 1 is equals to 3. Okay, here 1 is playing as a identity element. So okay, it is satisfying the identity problem. Next, inverse. What is inverse? Inverse is A into A inverse is equals to 1. So we know formula for inverse, A into A inverse is equals to A inverse into A is equals to 1 here. So for what elements you are getting this as 1? 1 into 1, you are getting as 1 as the identity element. And even 3 into 7, here you are getting the identity element. Here 7 into 3, this is the identity element you are getting. 9 nines are 81. For this you are getting the identity element. So whatever we have, so 1 inverse is 1 here, 3 inverse is 7 here. Here 7 inverse is 3 and 9 inverse is 9. So that means 1 into 1 inverse is 1, 3 into 7 inverse is 1, and next is 7 into 3 inverse is 1. Okay. So with the help of this, you can say that even inverse property is also satisfied. From the table, it is clear that it is clear that 1 inverse is equals to 1, 3 inverse equals to 7, 7 inverse equals to 3, and also 9 inverse equals to 9. Okay, that means 1 inverse equals to 1 means 1 into 1 is equals to 1. Okay, this one is 3 into 7 is equals to 1, and this one 7 into 3 is equals to 1, and here this is 9 into 9 equals to 1. Okay, so here you write multiplication modulo 10, multiplication modulo 10. So like this, you are finding that inverse property is also satisfied. Next, what we have, 4 properties are satisfied. Last one is the commutative property. Commutative property is A into B is equals to B into A. So commutative property is also satisfied. So therefore, Zn is a abelian group. So fifth one is commutative property or commutative axiom, we can write. Okay, from the table, it is clear that about the principal diagonal, the table is symmetrical. Therefore, commutative property is satisfied. Okay, so you can see here that symmetry means we know that the transpose of that A transpose is equals to A. In matrices, we have seen A transpose. If it is equals to matrix A, then we call that it is a symmetry matrix. So it is following the same one whenever you take these all values, this one as a 4 by 4 matrix, and when you interchange them as a rows as columns and columns as rows, you will get the same matrix here. So therefore, it is following the symmetry in the table. And even here we have diagonal of 1, 9, 9, 1. And also here 9, 7, 9, 7, 9. And here also 7, 9, 7, 7. So like this, whatever the elements are there, those elements, they are following the symmetry rule. See, like this you can tell. 1, 2, this one, this one, this one. 199, and also even we have here 379, here also 379. Okay, here 917, 917, here also 917. Okay, so like this 3, 3, here also 3 and also 3. So even 1 and 1. So it is satisfying the symmetry property. That is, symmetry means A transpose is equals to A, and whatever the diagonal is there, the diagonal, principal diagonal, the table is symmetrical. Therefore, commutative axiom is satisfied. From the table, it is clear that about the principal diagonal, this is the principal diagonal, okay? principal diagonal, the table is symmetrical. Therefore, commutative property or commutative axiom is satisfied. Okay. So 1991, 379, 379, 1717. Here 17, here 17. Whatever the elements are there, 17 and also 33. This is 33. Are symmetry in table. Therefore, Z10 comma multiplication modulo 10 is an abelian group. Okay. So the symmetrical elements are here. You can take 1991. Okay. Next 379 and one more 379. Next 1717. Next 33. Okay. These all elements are symmetrical to each other. Okay. So therefore, commutative axiom is also satisfied. All the 5 properties are satisfied. Therefore, it is an abelian group. Okay. Next, we have the concept of that is elementary properties of a group. So in elementary properties of a group, we have what are the cancellation laws are there. Left cancellation law is there, right cancellation law is there. This is the very important. That is in solving many of the theorems, we use these two laws. That is the cancellation laws in the left side and also right side will be there. Two cancellation laws. Okay. Next, we have the idempotent element. Just if you know the definition with respect to of that, you can solve the problem. In cancellation laws, main you have the properties of elementary properties of a group are there. Based on that, you have two theorems are there. These two are very important theorems. You may be getting for 5 marks question. Okay. So elementary properties of a group. Okay, next is the right cancellation law and also left cancellation law. Elementary properties of a group. Elementary properties of a okay. So in that we have the concept of what is the cancellation laws. So cancellations are in that we have right one and also left one. Okay, let G be a group and A comma B comma C belongs to G. Then the following laws hold. Then the following laws hold. First one is the left cancellation law, that is AB is equals to AC. Plus here in both we have common A. So here we are cancelling this A and also this A. Okay. This is the left side, no? This is the left side and this is also left side. When you cancel these two on the left side, we call it as a left cancellation law. Left cancellation law. Okay. Next, right cancellation law is, that is BA is equals to CA. So A is on the right side. This is the right side and this is the left side. Here also right side A and this is the left side. When you cancel this A on both of sides on right side, then we call it as a right cancellation law. Okay. So right cancellation law and left cancellation law, with the help of this you can see the some theorems will be there. So the main elementary properties of a group are that in any group G comma dot we have the following. Okay. This is the important one. In any group G comma dot we have the following. We have the following. First one is the identity element is unique. The identity element is unique in G. Okay, in group G. So this theorem proof you have in page number 2.2.9. Sorry. That is whatever you will have the exercise side, you will have the number, no? That is 2.2.9. So that is the proof for this theorem. Next one is each element in G has unique inverse. Unique inverse. This is 2.2.10. Okay. So proof of this theorem and also this theorem you have in 2.2.9 and 2.2.10. So the main elementary properties of a group are, first one is the cancellation law and second one is the identity element is unique in G. Third one is the each element in G has unique inverse. These three are called as the elementary properties of group. Okay. Next we have idempotent element. Idempotent element. Idempotent element. So in this, so you have the definition of this one. Just wherever, anywhere, by doing the theorems or by doing the problems, you can identify what is the idempotent element in that. Okay. So if A is an element, in a group G comma dot such that A into A is equals to A. Okay. So the representation of idempotent element is A into A is equals to A. So you can see here that what will be the value of A such that when you multiply with A, you will get the resultant in A. Okay. So one A is A here, but what will be the another A? Okay, simply you can think that whenever one element A is there, if you want to get the same element as a resultant, Then if it is a multiplication operation, then compulsory A will be the identity element, that is 1. So that means A into 1 is equals to A. Here also whatever A is there, second A, that will be the identity element here. Okay. So that is called as idempotent element. Okay. Then A is called the idempotent element. Okay, if small a is idempotent element, okay, you can write element or idempotent in G comma dot. Then okay, we'll write here down. Then A dot A is equals to A if and only if, okay, the symbol no, it is a if and only if A dot A is equals to A into E is equals to if and only if A is equals to E. Okay. So A into A is equals to A if and only if what we have A into A. A into A is equals to this A. What is A? A value is you are writing identity element E implies. So what from this two we can tell that A value is equals to E, where E is the identity element. Okay. So you can write this as hence for A belongs to G, A is idempotent if and only if A is equals to E. Okay. So we call A as idempotent element whenever this A value is equals to identity element E. Okay. So means identity element is nothing but A value is equals to E, and whatever the here resultant is there, that is A into A is equals to E, then we call that A is idempotent element. Next, we have one problem. This is the important one. So this is regularly asked for the 5 marks question in the section A. Even sometimes you may get for the, it may be asked in 10 marks question also. Okay. That is, let Q plus be the set of all positive rational numbers and define a binary operation star on Q plus by A star B equals to AB by 2. Prove that Q plus comma star is an abelian group. You have to show that there is a set of positive rational numbers with respect to of some, it is defined, AB is defined in some form. With respect to of that, you have to show that it is an abelian group. That means you have to show that it is satisfying all the 5 properties. If it is satisfying all the 5 properties, then it is an abelian group. So next, this is the problem. Okay, next one is the problem we have, that is let Q plus be the set of positive rational numbers rational numbers and define a binary operation star here, okay, star on Q plus, okay, by, so this binary operation is defined as A star B is equals to AB by 2, okay. Prove that Q plus is Q plus comma, what is the operation here? Operation is star here. Prove that Q plus comma star is an abelian group. Okay. So abelian group means compulsory, commutative property, and all the other 4 properties it has to satisfy. So here star in the solution you can write star is a binary operation on Q plus. Since AB by 2 is a positive rational number, whenever A and B are positive rational number. So this, whatever the sentences are there, you can write from the textbook. It is in page number 36, 2.4.2. We have, that is exercise problem this is. So you can write those sentences. So star is a binary operation on Q plus. Star is a binary operation on Q plus, okay. On Q plus, since A by B is a positive rational number, okay. Whenever A and B are positive rational number, okay. So A and B are the positive rational numbers. Therefore, AB by 2 is also a positive rational number we have. So first property is the closure property. So closure property means what here we have A star B is equals to AB by 2. Whenever you do the multiplication of those two elements, whatever the resultant you are getting, that resultant is present in this. So therefore, closure property is satisfied. So next we are going for the associative property, that is for any okay, for any A comma B comma C belongs to Q plus, okay. A star B, B star C, okay, we know this. So A star, so BC is whatever the definition given here, that is A cross B, you can take any numbers. If you do the A star B or B star C, the resultant should be AB by 2. That means BC by 2. Okay. So you are getting this, and now it is in the form of this is A, this is whole thing is B. Again A star B. So A star B is defined as AB by 2. AB by 2 means A, B, C by 2 by whole 2. Okay. A, B, C by 2 by 2. Okay. So it is equals to A, B, C by 4. So this is 1. Okay. So next if you take A star B star C. What is associative property? A star B star C is equals to A star B star C. Okay. So A star B means it is AB by 2. And again star into C. This whole thing is A and this is B. So A star B means again it is defined as AB by 2. That means it is equals to ABC by 2 by 2. So it is equals to ABC by 4. This is 2. So therefore 1 is equals to 2. That is A star B, B star C is equals to A star B star C. So it is satisfying the associative property. Therefore, star is associative. Means it is satisfying the property of associative. Next, the second one is identity. So identity means whenever you multiply with A, that number you have to get the same A value. Okay. So that number should be, so with respect of it is a multiplication, A into 1 should be equals to A here. So A into 1 means whatever the definition is there, A into B. That means A by 2 you have to get. So A into 1 means this is by the definition A by 2. So when you multiply with 2, this 2 will get cancelled. You will get the value as A. That means here 2 is called as a identity element to satisfy the property A into 1 is equals to A. Okay. So the number 2 becomes the identity element. The number 2 becomes identity element in Q plus, since A into 2 is equals to A. A into B. Here what is A into B is defined, it is AB by 2. Okay. So AB by 2 means A into 2 by 2. So this 2 if gets cancelled, what you will get the resultant? It is equals to A. Okay. Next to 2 into A. 2 into A is equals to 2A by 2. So this 2 will get cancelled, you will get A. So in both the cases, you are getting the same. Therefore, A star 2 is equals to 2 star A is equals to A. So here what we call identity element, 2 is called as a identity element. Okay. So here identity property is also satisfied. Next to what we have the inverse property is there and also commutative property is there. So inverse property means what we know. Inverse is A into A inverse. A into A inverse is equals to 1 you have to get. So what is our identity element we have got here? So A into A inverse you have to get as 2. Okay. So with what if you multiply A, you will get the value as 2. That you can check. First one is A. So A inverse value should be 4 by A. 4 by A means what you will get? So this is A into B. A into B means again it is defined as AB by 2. AB by 2 means this A will get cancelled. A means 4 by 2 will get, it is equals to 2. Where 2 is called the identity element. Okay. So next one is the inverse. Okay, next inverse property. For any A belongs to Q plus, 4 by A is an element in Q plus. Okay. So if A belongs to Q plus, then 4 by A. Why? Because it is a rational number is defined as in the form of AB by 2. That means it is in the form of fraction. Okay. So therefore 4 by A is an element in Q plus and A star 4 by A is equals to. This is whole thing is A and this is B. So A star B means what is defined in the question, that is A star B is equals to AB by 2. So B is here 4 by A and whole divided by 2. So this A will get cancelled. So 4 by 2 is equals to 2 you are getting. So similarly 4 by A star A is equals to 4 by A into A by 2. So A will get cancelled again, 4 by 2 is equals to 2 here. So you are getting the identity element 2. That is A into A inverse is equals to 1 or A into A inverse equals to 1. So in our problem, identity element is 2 here. So we are getting the identity element 2 with respect of A star 4 by A. So 4 by A is called as the A inverse. Okay. So therefore A star 4 by A is equals to 4 by A star A is equals to 2. Hence 4 by A is inverse of A in Q plus. Okay. So 4 by A is called as the inverse of A in Q plus. Last one is commutative property. So commutative property is AB is equals to BA. So for any A comma B belongs to Q plus, A star B is equals to. A star B means what you will write? AB by 2, no? So you can write AB by 2 as BA by 2. In multiplication, you can interchange the numbers. So here you can write BA by 2. It is equals to B star A. Okay. So A star B is equals to B star A. Therefore, commutative property is satisfied. Therefore, star is commutative. So last one you can write Q plus is an abelian group. Therefore, Q plus is an abelian group. Therefore, Q plus comma star is an abelian group. Because it is satisfying all the 5 properties. So this is the important problem. So it is regularly asked in the examination. So by this topic, we are completing the unit 2. So tomorrow we'll start the unit 3. It is a subgroup and also cyclic groups. Okay. Okay, once you see the other important theorems in the second group, that is the page number 35, 2.3.5. This is also important one. And next 2.4.3 problem. Let G comma dot be a group such that x square equals to E for all x belongs to G. Then prove that G comma dot is an abelian group. And 2.4.4 is very important one. This is the regularly asked for 5 marks question. Prove that a group G comma dot is an abelian if and only if AB whole square equals to A square B square for all A comma B belongs to G. Okay. And most important and regularly asked question for 10 marks, 9A or 9B question. It will be 2.4.5 question. Okay. This is very regularly asked for 10 marks question. 2.4.5. Let G comma dot be a group. Prove that the following are equivalent. Whenever equivalent question is asked, means whatever here the numbers are given, that is 1, 2, 3, 4 are there. No? So they each and every whatever the statement are given, they should be equal to one another. So 1 should be equal to 2, 2 should be equal to 3, 3 should be equal to 4, 4 should be equal to 1. So then only we call it as a equivalent group. Okay. So equivalence relation will be there. No, A equals to B, B equals to C, then A equals to C. There is a transitive property. So equivalence means it has to satisfy all that. There is a transitive property, reflexive property, and also symmetry property. So like that only equivalence whenever given as like this. So first one, whatever the first question is there, that is G dot G comma dot is an abelian group. It should be equal to, we have to show that it is equals to AB of whole inverse equals to A in a B inverse. Then second one is implies to third one. Then third one implies to fourth one. Then fourth one implies to first one. Then we call it as a equivalence. It is satisfying the equivalence property. Next, 39 page number, you have finite groups. I have told the definition of what is infinite and finite group. So one problem is given 2.5.3 on finite group. Next 42 page number, that is theorem is there 2.5.8. Let A be an element in a group G and A is finite order. Let M be any positive integer. Then A to the power of M equals to E if and only if order of A divides M. So sometimes this question may be asked for 5 marks question. Okay. So 1 10 marks question you will get from the unit 2. And other than that, those are the 5 marks questions. So by this we are completing the groups, that is the second unit. So it was a very lengthy one. You can see all the important problems or important theorems I have told. So try to practice them. So tomorrow we'll start what is a subgroup definition. Depending on that, you have some theorems are there. Important theorems are there for the subgroups. Elementary properties of subgroups are there. And one important theorem in this is that is the intersection of any two subgroups of a group G is again a subgroup of G. And in this two or three 10 marks questions are there. Okay, 1 10 marks question you will get in the second unit and one more 10 marks question you will get in the third unit. Okay. So 10 marks questions are 3.3.6. Okay, this is one, and next 3.3.7. This is also very important and also regularly asked in the examination. So these two in subgroups, 2 10 marks questions, and also next we have in this only cyclic groups are there. In cyclic group you have many important theorems are there. Okay, so any one you will get for the 10 marks question, and some 5 marks small questions are also there here. So you may get 1 5 marks question also in the topic cyclic groups. So page number 60, you have every group, subgroup of a cyclic group is cyclic. This is a regularly asked question. You will get for 10 marks question. Every subgroup of a cyclic group is cyclic. So these are the one is 3.4.9. Next one, this is the small one, and sometimes it may be asked for 10 marks question also. That is every cyclic group is an abelian, but the converse need not be true. Okay. This is also very important. Repeated question you will have 3.4.5. So 3.4.5, 3.4.9. These two are 10 marks question in cyclic groups. 3.4.5, 3.4.9. So definition of cyclic group or subgroup is important. Sometimes it is asked from the question also. So these are the important topics here. Third unit. So tomorrow we'll see what is the definition of a subgroup, what is the definition of a cyclic group, what is generator. We'll understand those concepts. With that you will complete the block 1. Okay. So tomorrow we'll complete block 1. Sunday we'll start the block 2. So that is groups. Unit 4 we have Cosette's and Lagrange's theorem for finite groups, normal subgroups and quotient groups, homomorphism and permutation groups. Okay. So tomorrow we'll see the third unit, depending on the what are the subgroups and also what are the cyclic groups. This is the most important topic. So definitions are important. If you know the definitions, then only you can do the proof for the theorems. So that's why try to learn the definitions for solving the problems and also theorems.